recording. There we go. Okay, good morning. So before we start, I'll just say that for today's lecture, you should download a file which is in lecture notes and codes in Blackboard, lecture codes, and down here, GradDesk V0. Okay, so it's a very small file, but it's handy to have it just ready. Okay, and I'll open it in Spyder immediately, as soon as I can find it. There, well, desk V0. There we go. This file here, okay. Also this one. Good. So you had a couple of theory lectures by now, and today and then next programming lectures, we'll start trying to implement part of what you've seen in the theory lectures. And in particular, we are going to implement gradient descent, or also called steepest descent, which is one algorithm that's one basic algorithm which is used for continuous optimizations, and more specifically, unconstrained continuous optimization. And so we are going to start, of course, from the simplest cases when we start our implementation, as it's usually best practice to do, and we'll start from the one-dimensional case. So, sorry, no, there. So just to refresh our memories and set down some notation. So gradient descent. Well, I might make the effort. Okay, so we start from the 1D case. 1D case, meaning that we are dealing with functions that go from R to R. Okay, so our goal is to find the minimizer. I mean, as I was saying, it's unconstrained optimization. So here the domain is not a subset of R, as you will see in the general theory lectures. Here I'm just saying that the function has values for all real numbers. And the task is find the minimizer. So find argmin of x, of f of x and f of x, okay? So this is our goal, essentially. Now, as you know, this is a hard problem in general. I mean, it's not trivial to do it at all. In particular, many methods, and most relevantly gradient descent, they don't guarantee that you find the minimum of a function, but they can guarantee, under some appropriate circumstances, that you can find the local minimum of a function. So, so you're given a function. Let's have two examples maybe here on the sketch so that we can. So this is the first one, and then the second one. Oh, sorry. It's really not very comfortable to draw graphs here in this position, but anyway. So you have a couple of situations. So first, something like this, right? Looks like a parabola. It's not necessarily a parabola. I'm representing a complex function there. Of course, a parabola could be such a complex function. And then you could have something like this. Okay, just a second example. Well, sorry, that could get confusing in a while, so let me do it this way instead. Okay, something like that. And of course, well, where's the minimizer? Here it is. And here it is in these functions. Hope you can see it, I guess. Yeah. Yeah. And of course, however, there's a local minimum also. So something here, which, depending on the actual real problem that you're trying to solve, may or may not be acceptable, okay? So in general, our goal is to find the global minimizer. But just as we've seen in other optimization problems, which were of a different nature from this, where they were discrete, but think of the traveling salesman, you could find many so-called local minimizer. You couldn't represent those as in a graph like that. But in that case, we had algorithms, in particular, simulated annealing and gradient descent, which were able to give us local minimizer under some appropriate notion of what local means in that case. Here we have all the analysis to tell us what's a local solution, right? Because you have neighborhoods of points and so on. There's a topology here. Anyway, intuitively, it's pretty clear that in the traveling salesman, we got local minimizers, some of which were very, very close to each other in terms of the costs. And so maybe, depending on the actual problem that you are trying to solve, maybe getting a slightly suboptimal solution, it's not such a big deal. In other cases, it might be. Depends, really, okay, on your application. And also, of course, it depends on the shape of what you're doing. Here, in this second example here, the other local minimizer, I don't know, is that very much higher than the true global one? Again, it depends whether you can accept that gap or not in your application. So it all depends, all right, on what you're actually trying to achieve. But mathematically, we have methods to get us to either of those two minima, okay, the local or the global. Okay, so after this, let's say, oh, and by the way, of course, just in case any of you is wondering, here I'm doing the one-dimensional case. So for the one-dimensional case, it's very common that you could just draw the graph, like I did here. Okay, you have a function, you just evaluate, right? At many, many points. You draw the graph, you look at it and say, there's the global minimizer. Okay, problem solved. Now, this is, of course, the reason why we are doing all of this with a, say, more sophisticated method than just look at the graph is because in high-dimensional case, that doesn't work at all, okay? It's not only because we want a precise answer, it's really because you just cannot do this in. So, for example, here in one dimension, imagine drawing the graph of a function in one dimension within a range. What do you do? You divide the range into, I don't know, 1,000 steps and evaluate the function at each point, and you look at the shape. Now, suppose that you're doing it in 2 dimensions. What do? You divide, you have now a square, where you want to plot the function in, and there you have 1,000 by 1,000 points, so that's 1,000,000 points that you need to evaluate the function in. If you're now trying to do it in 3 dimensions, you have 1,000,000,000 points. In n dimension, you have 10 to the 3n points, which of course, doesn't scale up very nicely. As soon as n is, I don't know, 30, you're already out of your depth, all right? Okay, so just to be sure that everybody is clear on that. So we are doing this, of course, one-dimensional case as an example of something that is going to work for larger dimensions. Okay, having said that, where were we? Yes, so this is the problem. We are going to also have a couple of assumptions, again, just to keep in mind, so that, well, we are going, now, in these lectures, I'm not going to necessarily be very precise in terms of mathematical notation because that's not my focus. That's the focus of the theory part, okay? So here I'm trying to bridge, in a sense, the gap between the mathematical part with all the theorems and the coding part, which is where we put things in practice. And so I'm going to say, provide some mathematical statements which are not entirely precise, but hopefully give you an idea, and then you can go back and look at the theory part to see how they're spelled out precisely. So find our mean, we are going to assume that assuming it exists, and is finite. So we are assuming that our function, somehow we know that our function is not going to drop at minus infinity at any point. All right? This is what I'm saying here. Okay, so which method did you see for solving this particular problem here? One-dimensional case, find a minimum, find the global minimizer, or at least one local minimum. Which methods did you see? Newton? And the second method. Okay, so now we are actually going to do something more primitive than either of those. Okay, we'll start with something which is gradient descent. So you know, I think that this was mentioned. This was mentioned, I think, for the multi-dimensional case. You'll see a formula that's going to look a little bit familiar to you. So it's an iterative method, just like Newton. And in Newton, you know that you have an iterative method, so you actually do something like this. Well, did you write it this way, perhaps? Something like this, as a general formula. So you have your point at x, sorry, this k is not an exponent, right? This k is supposed to be an iteration index. So you start from some x0. Let's spell this out explicitly. So you choose x of 0, your starting point. And then then you set k equal to 0, and you apply some formula like the one below, where every time you update your xk by some quantity and you get the next one. All right? Okay, in Newton, that pk, oh, sorry, and there's also this alpha here. So did you see a notation like this or not? Something like that. The line search. Okay. Yeah, that was the multidimensional case already. Okay, good. So, good. That gives us a bridge point, okay, from the theory to this part here. Now, you've seen in the multidimensional case that you can pick you are at some point, you pick a direction in the space, and then you say, okay, now that I've chosen my direction, I want to move along that direction and somehow find the minimum where there, or something like that, right? Now, in this case here, we are in the one-dimensional case. So picking a direction is fairly easy. Just one. You just go along the line. So you could do the same, except we are still have the problem of finding the minimum along that direction. Now, the method of line search is to restrict yourself to that one single dimension, and then find the minimum there. Find the minimum how? Maybe with Newton or something. Here, we are going to use, as I said, a more primitive method, but it's going to look the same. So actually, it's going to be like this. This maybe this is going to to sound a little bit familiar. So here in gradient descent, we set this to minus the derivative. Well, it's the one-dimensional case, so I can write the derivative like this, evaluated at point xk. And this alpha here is strictly larger than 0. So it's a real number. So let me say it's in 0 infinity, something like that. Good? Okay, so this is what was called step or learning rate, or something like that. Did you see? Did you get this right? Okay, good. So this is a step. And this is, I mean, in the one-dimensional case, that's the derivative. Now, I'm going right away to start calling it the gradient, even if we are in one dimension. Just because, as you know, the gradient is the generalization of the derivative in more than one dimension, where the input has more than one dimension. So I'm going to call this a gradient. Okay? And now, of course, that means, well, maybe you can see it in action. That means that given some function like this, you choose an x0, I don't know, maybe this one here, maybe 0, you know. You don't know what to choose. You can choose 0. I don't. It's not. Okay, I'm saying this is x0. You can choose whatever you want. So there, at that point, you compute the derivative. Now, the derivative in one dimensional, you generally represent it with a slope. So something, can you see it? Something like this. Okay? Now, in the Newton method, you would also use the second derivative and try to approximate that red line there, that red curve there. You would try to approximate that using the first and second derivative, using the Taylor expansion. That means approximate that function there as a parabola, and then analytically find the minimum of the parabola and move there as your next best guess. Now, in this case here, we are doing something more primitive, as I was saying. It's just saying, well, given that this gradient there, that's negative in that point that I just drawn, okay? The gradient is negative. If the gradient is negative, it means that in order to decrease the value of my function, I need to go right. Good? Just if it was on the other part, if you have a positive derivative, you just need to go left. So you just go in the direction opposite to the gradient, essentially. Now, also, the steepest it is, the larger the gradient in absolute value, the quicker it decreases. And so you move along that direction. So you move along the direction proportional to the opposite gradient, to the negative gradient. So maybe, you know, I can say right here, this is the negative gradient. You move in the direction of the negative gradient proportionally to the negative gradient with some step. Now, this method here, it guarantees, assuming that the function is smooth and differentiable and all those things, it guarantees that if the step size alpha is small enough, then you will eventually, iterating over and over, you will at the limit, you will get to a local minimum. Okay? So by doing this, xk plus 1 equal xk minus alpha df. I'm going to write it like this, even though, again, we are in the one-dimensional case. Doesn't matter. df of xk. Okay, so if alpha is small enough, then in the limit of k going to infinity, of infinite number of steps of this procedure, you get to some, well, I don't know how to write it. I mean, to local minimum. Local minimizer of f. Okay? I don't want to use the too heavy notation here. Just okay. So you're guaranteed to find at least some local minimizer. Let's see this, and let's code this. Okay, this is looks pretty easy to code, right? I mean, should be pretty easy. I mean, it's one of the easiest formulas we've ever seen, but it's going to give us a few interesting points to something interesting to say about the programming part already. Okay, so everything's clear so far? Hopefully, yeah, good. Okay, so here I have some code prepared, and there are 3 functions there. You see defined already. There's g. G is a polynomial. It's the polynomial of 4th grade, x to the 4 plus 4 times x to the 3 plus x to the 2 minus 10 times x plus 1. 4th degree polynomial. Now, I've already written analytically, because this is a polynomial and it's easy, I can easily find out its derivative, which, again, I'm calling gradient. It's 4 times x to the 3 plus 12 times x to the 2 plus 2 times x minus 10. Good. Now, I also have another function h, which and k. Those, ignore those for the time being. Okay, we'll look at them later. Okay, by the way, so we are going to try to find a minimizer for this function here. And for g, of course, you know analytically that you could set just the gradient of g to 0 to solve it. And then maybe find all the solutions that there are, if there are any, and then maybe look at the second derivative to see if it's positive. So all this stuff that you know from analysis, from calculus. However, this is already a 3rd order equation, and I'm willing to bet that none of you knows the formula for 3 3rd order equations, even though it exists. So, I mean, nobody studies that. It's very complicated, or almost nobody studies that. Anyway, so we're going to solve it numerically. And okay, so first things first, we try to plot this function. Now, as I was saying before, here, the way we plot the function is just take a range. I mean, I used -5, 3 here. It's just a reasonable range for this function. And divide that range into 1,000 points. And this is what linspace does. We've seen this towards the beginning of the course. Okay. And now here there's something interesting already. Look at this. Well, at least, let's say it's interesting with respect to the conversion of math to code and vice versa, translations between math and code. Okay, here, xv is an array. G, here, I was describing g so far as a function. Okay, I've been describing g all this time as a function from R to R. So, what happens if I have a function in general that takes real numbers and I give it an array? Normally, you would expect that not to work, right? Because the function is expecting 1 number at a time. You give it 1,000 numbers, in this case, shouldn't work. However, purely because of the way this function is written here, observe how g is written. G is written as a polynomial, and in particular, it uses exponentiation, like to the powers of 4, 3, 2, and it uses multiplication by scalars, like taking something by multiplying something by 4, or by -10, or by 10, and additions and subtractions. And also, there's an addition to a number. All of these operations broadcast. So if you now give an array here as the input, then x to the 4 is going to be an array with all the elements taken to the power of 4. Same for x to the 3 and x to the 2 and so on. So when I call this here, here's what's going to happen. There's an array xv. This operation here, that's the order in which things happen. This operation here will create a new array, okay, with all the elements elevated to the 4. This operation here will also create a new array. Another. Now, multiplying that by 4, that gives you also yet another array. We are a third array now. Then there's this sum here, which happens. That sum there creates yet another array. Then this happens, one more array. Then this sum, I mean, whatever was computed before gets summed up with this. This gives you an array again. Then there's 10 times x, one other array. Then there's this subtraction happening, another array. And finally, plus 1. You have an array, you add 1, you get another array. Okay, so all of this broadcasts, and the net effect is as if you had applied the function g that you think of as a function from R to R, is as if you had applied that to the array one element at a time and put the result in a new array. Yes? That's a good question, and we'll see it when when we actually do that. Okay. So far we are. That's a perfectly valid point. Yes. So, but just to comment on this, of course, this that I just demonstrated is going to broadcast on the dimension that you give it, and therefore, if you wanted the function to actually take the whole array and give a number, and you wanted to do it repeatedly for many input arrays, then what could you do? I guess give it a matrix or something like that. That's one thing you could do. Okay? Yes? Okay, the question for those at home is it more efficient to use broadcasting or a for loop? Okay, this is a good point. In Python, for loops are pretty slow and inefficient. So in the absolute sense, if you had to write this in a way that runs the fastest possible way in the hardware, you would do something which is basically a for loop. So you wouldn't have all these intermediate arrays that I just described before. You would actually go and take one element at a time, do the computation. I mean, you just prepare a new array for the result and go one element at a time and compute it. And that would be a for loop. Okay, but in Python, if you write it that way, it's kind of slow. In Python, broadcasting is way more efficient. It's just, broadcasting is basically for loops, but written in C underneath, okay? Yeah. Yeah, broadcasting is essentially a hidden loop. I mean, it's a more convenient way to write a loop. It's more convenient in the sense that it's generally shorter, like here, I don't need to write it, okay? Actually, explicitly, it's automatic. Why, sorry? Okay, the question is why, sorry. Yeah, I need to relay the question because people at home are not going to hear. So the question is, well, if broadcasting is more efficient, why would anyone use for loops at all, essentially, instead of just using broadcasting all the time, which is basically for loops that are written in C. Now, does anybody want to attempt an answer to that? Any idea? Does anybody have an idea why you wouldn't just use broadcasting all the time? Why are normal for loops as fast as broadcasting ones? Yeah, good. Yeah. Yes, okay, so this is, we are getting a little bit technical, but it's perfectly fine, it's good. Okay, so, sorry, scratch that. The question is then, why aren't normal for loops written in a way that's just as efficient as broadcasting? And the reason is, the real reason is that Python was developed in the 90s. I mean, in 1992, I think it was the first version or something. At that time, there was a trade-off between speed and convenience, in a sense. When Python has been designed for the first time, it was designed with the goal of saving the time for programmers and not so much for the hardware. So it was designed with having in mind the fact that the programmer might want to do whatever, many different things in a dynamical way, in an interactive way, so on and so forth, with, say, high-level objects and so on. Now, because of that, they made some design decision, and now every time you call a for loop in Python, Python just cannot know in advance, cannot figure out in advance how to optimize the thing that you're trying to run very efficiently. And I mean, that's normal Python, because the rules of the language are so permissive that many different things might happen inside the loop. And when a loop runs, you could have, say, variables changing type, and even new functions that change their definition in the middle of the loop, whatever, okay? So because Python is designed to be very, very permissive and dynamic in nature. Whereas when you do the same for a broadcasting loop, in a sense, it's much safer, because as soon as you start doing the operation, you know how long the array is, you know that each element has, I mean, a type, in this case, a floating point type of a specified bit width. It's always the same. You know how to translate all of that into very optimized hardware instructions and that wouldn't be possible for normal for loop in Python, because in a normal for loop in Python, every time that you're trying to do an operation, you need to check, is this still a float? Am I still doing this particular 3 CPU instructions, or should I do something else? Has this immediately suddenly become a string or whatever? Okay, so that's the idea. Now, having said that, there are ways to actually do what you were trying to ask for, basically having for loops, which are also fast. Well, in C, of course, but that gives you a restriction, because C is much more limited and less dynamic and so on. There are other possibilities. One is to use something called PyPy, if I remember correctly, is a different interpreter for Python. It's just-in-time compiled. It's a different way of optimizing the code, or even Numba, perhaps. Anyway, there are a family of approaches called just-in-time compilation, in which the code is analyzed and optimized in advance, in a sense, and then the analysis can be carried out by the compiler automatically, and that compiler can then determine whether the loop can be actually optimized effectively. That comes at a cost that not all of the language is supported. So you have a faster interpreter with some restrictions that it's not able to run all possible Python code. That's one way. The other way is to change the language entirely. There's a language called Julia, which I'm very particularly fond of, for example, which is like Python in the sense that it's high level, but it's much faster in the sense that it's just-in-time compiled, and the whole language optimizes everything that it can, more or less in the way that you were trying to suggest. Okay, good. Does this answer the question? Yeah, good. Good. So coming back to what we actually are using, broadcasting is faster than for loops in Python. NumPy arrays are faster in practice. There are ways to do it faster than this. One way to do it faster than what I wrote here, which is already fast enough, okay, let's say. But if you want to really make it even faster, what you would do is to pre-allocate the memory that you need for the output, or say some memory and some temporary memory, and then perform this operation without generating a new array all the time. You would needed to use the np.pow, np.mol functions, so NumPy functions, not the star operators. Okay, you would need to use those functions, and then provide the out keyword argument. The out keyword argument in NumPy functions says, you know what? Don't create a new array. Write whatever is the result in this array that I'm giving you. Okay, and that means that they can reuse memory. That becomes often that helps a lot with performance. So it cuts down running time by a large amount. And so it's not getting to what you, I mean, it's not getting to the same exact speed as you would have writing a C code, a very optimized C code that does exactly the same, but it's close, okay? Anyway, we're going obviously to use this because it's much more convenient. And so for this particular course, let's say that when I say write something efficiently, personally, I'm going to be satisfied with writing something like this. I mean, something that uses broadcasting in the proper way. Then if you want to be more advanced on your own, I mean, feel free, of course. Well, you can explore these issues in more depth and also, well, okay, so this was a kind of long discussion, but hopefully it helped clarify a few things. I don't know, maybe it obfuscated them, who knows. Anyway, so back here, we were saying that now this G, even though G is a function which was conceived as a function from R to R, now it takes an array and it spits out, of course, an array. And here I'm plotting it. Then the last thing here is a placeholder, of course, for a function that I want to write later on. And if you run this code, you see this function here, which is a function with two minima, just more or less like the one that I was drawing before, of course. And the goal would be to get to this minimum here, but occasionally you might get here. Good. So having said that, let's try to where were we? Let's try to put in practice this, right? So this here. Okay, so how do we write this in code? Well, how do we write this in code? Well, there's going to be x0, so let's start sketching out the overall structure, right? x0 equals something, and then you're going to have a for loop of some sort, okay? And then in the for loop, there's going to be, I don't know, x. You say xk plus 1 equal xk. I mean, here I'm not writing real code, right? Xk plus minus alpha times something, and then here return, I don't know, the last x, whatever. Okay, so this is more or less the general structure. Of course, it's written in a way that's not going to work in any possible way. But we just need to fill in the details essentially and write actual code instead of just words. Okay, but the structure is going to be something like this. Yes, at least to the bare bones. What, to do it? Recursively. Ah, a recursive implementation of gradient descent. Yes. Uh-huh. Good. So the question is, couldn't we do it recursively? Well, it's possible, but you know, when you have, I mean, it's not, I mean, it's an interesting idea. It's not a good one, unfortunately. Why? I mean, no, it's because of Python. It's not a bad idea in general. It's because of the way Python works. Okay, because when you do something recursively in Python, and actually in most other languages, I should say, then when you have a function that calls itself, it creates a new frame on the stack. You think it creates a new space for its local variables and arguments and return values. And then inside there, you call itself again, and it creates another stack. And and then that inside that the function calls itself again from that position, and it creates another frame. So if you have an algorithm like this, which, as you will see, it's going to, I mean, easily require thousands or tens of thousands of iterations to complete, then that would translate into having thousands or tens of thousands of stack frames in a recursive chain of calls that need to be there on the stack until you find the end, and then they get all destroyed. So that's a waste because of the mechanism, because when you call a function recursively in Python, it actually creates the frame. There are other languages which have an optimization for this case. It's called tail recursion. It's called, I mean, the general mechanism is called tail recursion. In any case, it's optimized precisely for this case to just avoid, I mean, you write it in a recursive way, it works as if it was creating the frames, but it's not actually doing that, and therefore it's as efficient as the thing that we're going to write. But in Python, we are going to write it with a for loop. Okay? Good. Okay, so what's the thing? Well, how do we do this? Well, the for loop, there are many ways that we could write it. What I'm going to do is I'll start with just the simplest thing that you can do. So the simplest thing that you can do is, I mean, at least in my opinion, is to say, well, look, my guarantee is that alpha should be small enough. Well, that's another matter. But my guarantee is that I need to go on long enough, okay, in the limit of infinite steps. I'm going to just do a large number of steps, okay, and that. Okay, so instead of infinity, I'm just saying going, how many steps? I don't know, 100, 1,000, something. I'm going to set a number of steps, all right? So I'm just going, just a second, I'm going to say for k in range something, okay? Say max t or something, some value, okay? And then, well, you know, you see that every time you have your point here, you overwrite it with a new estimate. And then at that point, you don't need the old one anymore, at least for this algorithm, not for this algorithm. You've seen the second method, you would need at least the 2 points at a time, right? But here we don't. Here we just can discard everything. So I don't even need to specify this k plus 1. I just can say x, the new x, is on the left, and on the right, it's whatever was the old x minus alpha times, well, some sort of gradient of the function at position x. Now, okay, so when we return, we are going to just return x, right? Okay, and then, well, what about x0? So we are missing a few things here. The gradient is something that we don't have right now in the code, as you can see. We don't have max t, we don't have alpha, and we don't have x0. So where do we get those from? Well, at least some of those needs to come through arguments, right? I mean, we need to give them ourselves to the solver. So what arguments are we going to provide to this function? Sorry? XV. Ah, right. So there's something I should have said before. So what I'm trying to write here, that's good. So what I'm trying to write here with this grad desc 1D, what is this supposed to be? It's supposed to be gradient descent, but what I want to write here is not gradient descent for one specific function. I don't want to write the gradient descent solver for the function g. I want to write something which is more similar to what we did with the greedy solver and simulated annealing stuff. So I want to have something that, such that you give it a function, whatever function, and it optimizes it. Okay, so it's going to be, it needs to be something which is a generic optimizer. So at the very least, we are going to need to give it the function to optimize. Okay, so this is the bare bones things. Now there are going to be more arguments needed here. Okay, so what other arguments do we need? Well, options, just like in the simulated annealing or greedy algorithm that we've seen. You have options to the solvers, like the number of steps. Yes. I'm sorry? Yes, that's a great observation. I mean, if you look at the function here, we don't even use the function, we just use the gradient. That's good. I'm still going to write f there for future purposes, but it's a perfectly valid observation. So what other arguments do we need? Well, we clearly need the starting point. Can the algorithm, I mean, we could not give it, And then maybe the algorithm could figure out the starting point by itself. But that's not a great idea. Why? Because you might yourself want to try different starting points. You might want to have, maybe in your application, you have an idea of what's somewhere a reasonable starting, a reasonable starting point. And then you want to optimize from there, right? So we are going to give it as an initial point, and of course, remove this line here. Okay, then what else do we need? Well, you can just look at the error. Max T is not there, so it's kind of the number of steps, and then, of course, grad f. I'm going to write grad f, also alpha, sorry, first alpha, and also I'm going to write grad f, I'm going to write it there. Okay? Well, what else? Undefined name x. Well, undefined name x, I had deleted the line, but now I just want to do this. Okay, x, initialized it to 0, then do the computation, max t times, return it. Okay, pretty easy. Okay, we can try to load the code. Of course, it loads. We can try to run it just to check whether there are errors. So grad desc1d. Now we give the function that we want to optimize, it's g. Then x0, what do we write as x0? Well, whatever. We can write, I don't know, 0.3, something. Doesn't matter right now. Grad f, well, the gradient of the function that we want to optimize, we know that because we have computed it. It's grad g. Maximum number of steps, I don't know, maybe try 100. And alpha, it's supposed to be some small number. What does it mean to be small? That's not clear, and that there's no general rule for that. It only needs to be positive. Let's say 0.01, but that could change drastically with the problem that you're trying to solve. So, yeah. I'm sorry? Yeah. Yeah. Okay, good. So yeah, so for the people at home, maybe you want to increase alpha if you want to be able to jump out of one local minimum and get to the global minimum, sort of like we did for simulated annealing. Good. Yes, but we are not going to do that. Here, for gradient descent, that increasing alpha would not be such a great strategy, or at least doesn't give you theoretical guarantees. Having theoretical guarantees is pretty hard. There's thousands of people working on this exact problem, sort of problems like this right now at this moment in the world. How to jump out of bad local minima and get to better global minima, that's a very important question, which is as yet, probably unsolvable in general, but at least in some circumstances, you try to find the best approaches. Increasing the step size, people actually use it in practice, but it's it works sometimes, let's say. Okay. Sorry? Well, it ends up wherever it ends. I think we can have a look at pictures and see what actually happens when your step size is not correct. Okay. Anyway, what we are going to see for this course is just the simple case in which you want to have alpha small. You want your gradient to go down gracefully and nicely inside the local minimum. And if you don't like that local minimum, then start over from a different starting point. Okay, that's going to be our strategy. So let's run this. You run this, no errors. It gives you a number, 0.75 something. If you look at the plot, 0.7 something is here, which looks just about right. Okay, and well. How do we know if it's right or not? I mean, we can inspect it again, just because, I mean, you can enlarge it as much as you want. At some point, you see that now at some point we're going to hit this discretization. Why is this not smooth anymore? Remember why? Because, yeah, with lean space, we divided in 1,000 steps, so we hit the resolution. If you wanted to be more precise with the plot, you would need a finer grained vector here for the plot. But in any case, you can see that probably 752 something is around about here, which looks kind of right. I mean, if you ignore these issues with the resolution that we had. Okay, so problem solved. Now, there are a few things that we might want to do. Yeah.
Instead of having argument at 0, why don't we set it as like optional argument and then have the option to randomly generate the stuff?
Good. So the question is, could we set the argument x0 to be optional, and then if it's not given, then the function chooses itself? Sure. Then, well, that testing many times, how many times you get into one minimum or the other, you can also do with this. I mean, you just write the sum. I mean, you just pick the several x0, and for each of those, you run the optimizer. So that's, but, well, okay, right. So let's say, I mean, we can start, indeed, however, the suggestion is good that we can have at least some default values for these things. And I mean, these are not necessarily good default values, but there are no generally good default values for this function, so let's just keep it that way. Now, in terms of writing a default for x0, it could be done, certainly. Yeah, that's an idea. You could say x0 equal none, and then, or if it's not given, then pick a random number in some range. But which range? Well, you could choose 1, or you could just start from 0 every time. If you don't give x0, just start from 0. Whatever. Many things are possible. I'm just going to leave it like this, okay? Just explicit all the time because this, I mean, yeah, I'm just going to leave it that way. Now, actually, I forgot one thing. I've been working on GradDesk v0. I wanted to keep that safe. So I'm going to save this as GradDesk, okay, which is supposed to be the working version. I will fix GradDesk v0. And now I also want to save a copy which called GradDesk v1, just as a backup, and I close it immediately, and now we can move on. Okay, so next important topic. Now, before we refine this function here, which can be greatly refined, no, sorry. Let's have at least some visual satisfaction from checking what this did. Okay, I want to plot, even though it's unnecessary, I want to plot the points that it has evaluated in between, just to see what happened. Okay, let's plot those. In order to plot them, I'm going to need an auxiliary vector. I'm going to collect them in a vector, right? And, well, this is going to be something like axis equal np, let's say, zeros. I pre-allocate a vector of size max t plus 1, y plus 1, because xx of 0, I set it to x0, the first one, and then the other ones, I do it this way, x of k plus 1 equal x of equal x, okay? Something like this, and then I'm also going to return, xx axis, okay? And this is going to be redundant in the sense that the last value in this array here is going to have also the last x. So This is not really a good practice. I'm just want to quickly get out all of the values that I'm computing in the middle. Okay, even it's not part of the algorithm itself. I just want it for plotting. So I just run this, and now if I run grad-desc, I'm going to get x and x's, let's say, okay, all of the intermediate step, and maybe x min, I don't know. Okay, x min is the minimizer, and now the x's, you see, now we started from 0.3, and then it started updating it little by little. It has started increasing it until at some point, as you can see, it wasn't, after this point here, it wasn't changing anymore, or at least it wasn't changing at the level of precision that we can observe here. Actually, each of those numbers has actually 16 decimal digits. They're just not all shown. So probably the last few digits were also getting adjusted in the last few steps. But in any case, this shows us, well, first, that the code is working nicely, as it's supposed to. Secondly, it shows us that it's probably overkill for this particular example to do 100 iterations. Probably we could do with less. But let's ignore that for now. I mean, that's good in the sense that 100 is enough. We've reached the fixed point, okay, which is the minimizer. If we hadn't reached the fixed point, that it would mean that we didn't have enough steps. So if we gave it, if you gave it 10 steps, or I don't know, if you finish here, you can observe that it hasn't finished converging to a fixed point. Okay, so now you can plot it, and of course, you can write plt dot plot. Okay, and what you can plot is, well, the axis. Then you want to plot the corresponding function values, which is g of x's, and as we just saw before, you can call it like that. And then I want to say with maybe like this, I don't know, with points and lines. There we go. You see, this is what happened. So visually, this is where we started from, the 0.3. Then, I mean, because the derivative was negative, it moved in the positive direction. It goes in the negative gradient. So it moved there. And then the derivative becomes smaller and smaller, which means that each step becomes smaller and smaller, okay? Until you get here, and you see the steps become smaller and smaller still. And in the limit, they tend, you see that they accumulate. Of course, here we are again hitting this problem that the blue curve that we plotted does not have enough resolution, right? The blue curve does not have enough resolution. We've seen it a moment ago. But if you keep zooming in, you see that the orange points there, they accumulate and accumulate and accumulate. And if you zoom in, you keep zooming in, you keep zooming in. They never end. Actually, at some point, they must end. Ah, there we go. You see? Oh, good. What's going on here? Here we have hit the floating point approximation limit. Here there's one, the last bit is dancing around. Okay, going up and down a little bit. Good. Okay, so this is it. Of course, now you can make a guess. If you started, let's say, from here, from -2, what would happen? You would start moving towards the left, and then you would end up here. Okay, let's observe something that was suggested before. What happens, look, what happens if instead of 0.01, I use 1 as alpha? Okay, I'm enlarging alpha, just as was mentioned before. What if my step is not small enough? You do it, out of range. What happened? An error, numerical result out of range. What does it mean? It means that there's some floating point operation that just shot to infinity, essentially, and some of these operations cannot be carried out. Overflow error. You see, we've overflowed. What happened? Well, maybe we can start analyzing, I don't know, the first 5 steps, perhaps. Look at the first 5 steps. You start from 3, so you start from 0.3, you see 3 to the 10 to the minus 1, and then you jump right, as we said, the first step is to the right. But here the step is so large that you get to 8. It overshoot. Okay, it went too far to the right, and then it started on and went to minus 3,000, and then to 14.8 billions. So it's getting crazy. Let's observe the same thing with a slightly larger steps, a slightly larger but not as large step. Here it looks like it's kind of working, maybe. I mean, it's jumping around. Let's see what happens. Let's do 10 steps. Okay, you see that it still looks like it's jumping around. So let me say reload the code and then plt dot there. Oh, there we go. You see what happens. Look, 0.3 was our starting point. Where is it? It's here. Okay, it's this one. Then it should move to the right, but the step was too large. So it went beyond the minimum. Now at this point, it starts to say, OK, now I should go left. But again, it overshoots. And it overshoots all the time and keeps jumping around. See? So this is something that just, you can see whether, you can try to see whether eventually it settles down to something or not. But for this particular example, interestingly, I guess, it seems to never settle at all. Even if I do 1,000 steps, look at this. It keeps jumping around, bouncing. Okay, it never settles down. Because this method only works as long as the step is small enough. What does it mean, small enough? You cannot really tell in advance. One strategy could be, if it's doing that, if you observe it doing that and never settling down, maybe just reduce the step or something. Yes, there's a question. That's a very interesting question, but no. That's absolutely some peculiar feature of this particular polynomial that I chose randomly. Okay, it would be interesting, I guess, to understand why it actually covers that precise range, and it seems to be stuck in the range but never settling down in that beyond that range. Not sure. Yes. Yes, but that happens essentially, well, the property of this range that is covered, I guess, is that the second derivative is always, think about Newton method. In Newton method, what would you say, what would you write instead of alpha? You would write 1 over the second derivative. Now, if 1 over the second derivative is too large, and now I'm substituting that, which would work, with alpha. Now, if alpha is too large, it means alpha is larger than 1 divided by the second derivative, which means that I'm having a problem in the sense because 1 over the second derivative is always smaller than 0.1 in this case. And so if the second derivative is large, if the second derivative is large, it means that the function is narrow. If the function is narrow, then in the gradient step should be smaller, because otherwise you overshoot. And so the property there is that we have in that particular region is that the second derivative is large compared to the step that we used throughout. And so it never finds a position where the second derivative is smaller than 10, essentially. So 1 over the second derivative is always Yeah, 1 over the second derivative is always smaller than 10. It never gets large enough such that our algorithm can settle. That's, yeah,
Points like the range,
yeah.
and the reason that they don't like flow out of the range is like the second derivative is the same.
No, I'm not sure what what defines this range exactly. I mean, what defines the boundaries? I suspect that the boundaries are, yeah,
Steps are now, for example, if you're on the right point,
yeah.
if it doesn't move more to the right, then we can say that it's more faulty to move to the right than to move to the left. So maybe it gets more steep. So it doesn't move more to the right. So it chooses to go left instead. So maybe the second derivatives are the same.
At this point here and this point there, I don't know. I should need to think about it. I mean, one thing is for sure is that the second, what I said about the value of the second derivative here, whether here, I don't think, because the positions here are the result of overshoots. So I think that this is the maximum point that you can overshoot from this left part and over. And so if you assume that you have a range between this point and this, the left part of the range, you see how much it can overshoot at the most. You will find that other range, and then you do the converse. You say, given that range, how much it can overshoot at most, and if you solve for consistency between those two ranges, that should give you the whole thing. I think. I think this is the way you characterize this. But anyway, this got us a little bit far away, but it's kind of interesting anyway, or at least hopefully so. Now, what happens, just for completeness? What happens if you write a very, very small step? If your step size is too small, what happens? Yeah, I mean, you just it just, I mean, it would work, but it would just require too many iterations. You see, it's very, very sluggish. Okay, so, oh, sorry, didn't want to do that. Okay, so this is, of course, not very interesting. I mean, it gets there eventually. Oh. It gets there eventually, but it's just very, very slow. You see, so you want your step to be large enough, but not too large, essentially. And you can experiment a little bit, or even if you're fancy, you might want to start trying to write your own adaptive algorithm that just observes what's going on and try to figure out whether it can increase the step or maybe lower it down, something like that. We're not going to do it, okay? But
No one adjusts those parameters, but they can still find the
when you use graphical. Yeah, okay, so for one-dimensional functions, at least, it's not hard. And of course, there are much better ways than to solve things than gradient descent. Newton, for example. For? Well, but 3 is still, I mean, it's not very different from, try 1 million. Yeah, so the kind of problems that are generally actually solved with gradient descent, because they are solved with gradient descent, not because gradient descent is a great method, but because it's the only one which is affordable. And this kind of method, it's sort of the last resort when your dimensionality is sort of 1 million or something like that. There are, look, one of the latest neural networks that was published and had very good, excellent results for processing natural speech. I think it has 175 billion parameters, 175, 1 to the power of 11 numbers. That's the dimensionality. So you see, you don't use a graphical calculator for that. I mean, that's extreme, of course, but that's the idea that we're dealing here. And for smaller sizes, there are definitely much better ways than this. Okay, and you can be more refined, and you can have heuristics, and you can make assumptions, and have locally adaptive algorithms that just have a look around and try to figure out in which situations they are before they do anything. These are called poly algorithms that try to do some exploration and determine which algorithm to use in advance before actually applying it by doing some exploration and analysis of the function themselves, something like that. Okay. Good. Good. Well, time's almost up, right? I think we had two interesting discussions too, and so we did not get very far, but we did solve the problem. At least, yeah. Let me leave you with this, I guess. We have 3 minutes. So let me leave you with this. Why did I want to keep this function f here? I wanted to keep it because I want to deal with situations in which I am unable, for whatever reason, I am unable to write down the gradient myself. Okay? What does it mean? It means I have a function, and which means a piece of code, okay? And a piece of code could include something very different from just powers and mathematical operations like this. It could have for loops, conditionals, whatever, creation of arrays, anything. Okay, it's generic function in the coding sense. And now you want, I mean, you know that that function is going to give you whatever input you give it. It's going to give you a floating point number. Okay, and you suppose that it's continuous and differentiable, even though maybe possibly very, very complicated. And you don't want to write, or don't know how to write, the derivative yourself. What do? You want the computer to do it for you. This is a general topic. We'll see it next time, obviously. It's called automatic differentiation. The easiest, by far, thing that you can do is use finite differences. You saw it in the theory part. Meaning, just use the definition of the derivative and with a small step. So I'm going to write it down and then give you some food for thought for next time. So the definition. Oh, sorry. This is annoying. Good. Back again. So just say, I mean, you know that the derivative of f prime of x, is written as the limit for, let's say, epsilon or whatever you want to call it. Let me call it delta x of f of x plus delta x minus f of x divided by delta x. And now in finite differences, what you do is just you scratch that and you say, I'm just picking a small delta x. Okay? Instead of taking the limit mathematically, which you cannot do in the code, you just choose delta x to be small, yes? Yes, yes, we'll see this next time. Yes, exactly. So let's do it. So let's say that the f grad, this is now a function that's supposed to compute the gradient of any given function f, or for at any point x with some level of precision, epsilon, I don't know, 1 to the minus, well, let's try 10 to the minus 5. Well, return f of x plus epsilon minus f of x, all of this divided by epsilon. Okay? Now this is a function that, again, takes a function of an argument as an argument, a position where you want to compute the derivative, a precision parameter to which I've given a completely arbitrary default value, but it's small, at least supposed to be small, and then there you go. You run it, you take your function g, say computed at 0.3, and you see this. You know analytically, the analytical definition is grad g 0.3, it's this value here. Now we can test our function, which is this. Okay, now our automatic differentiator gives us this, which is close, right? Not perfect, but close. Maybe close enough for our purposes. Maybe not. Who knows? Anyway, here's what I want to leave you with for next time. Just think about it. I mean, I'm sure. So you can take this and take the difference between the numerical, I mean, the automatic, the finite difference is 1, and the true one, and you see that the error is 10 to the minus 5. You can say, even say, take the absolute value, just in case, in case. And so you can say, okay, now what about if I reduce the epsilon? If I reduce the epsilon, that should get closer to the limit, so it should be better, mathematically, at least in principle, if you just look at the mathematics. And it is. And if you go further, then, oh, well, I can increase my precision arbitrarily, get to 10 to the minus 8. And, well, not quite. Okay, look at this. Look at this. You keep going down, look at this. You see, at some point, the precision keeps improving until it doesn't. And for this particular case, it happened here. Okay, we'll see this next time. In the meanwhile, you can try and think about why this happens. Okay, I'll stop the recording now because I'm ready. It was until 11:40, right? 50? Ah, we have a few minutes more. I was rushing to get to here. You seemed a little bit too easygoing. Normally, there's people already packing and ready to jump out of the class. Anyway, so why does this happen then? Why does this happen? So mathematically, you look at the mathematical formula, and you see this part here on the right should approach the part here on the left better and better the more you approach, you make delta x or epsilon, whatever you want to call it, the more this approaches 0. Yes? No, I mean, it doesn't have anything to do with this, okay? Yes, it's floating point approximation, and it's one of the best examples of, I mean, it's one of the biggest issues with floating points. It's the following. Observe. Observe what happens in detail. Consider a case where things, you observe that they are starting to fail, but they are not, I mean, yeah, so let's look at this, okay? Let's look at this one. This one here, what is it computing this? What this is computing, sorry. This is computing g of 0.3 plus epsilon. So 0.3 plus 1 e to the minus 12. If you look at the definition here, I'm using this, okay? I'm writing out that explicitly. Look at this, okay? And now you subtract this here, which is g of 0.3. You see? Okay, this is not a great example. Let me do the absolute same thing with 0.4 because it's just the same. I hope this will work. Yes. Okay, so let's look at this case, but it's exactly the same mechanism. Okay, so here you have this value here, so the value of the function at a slightly perturbed position compared to 0.4. So you see, now you need to take the difference between this and this. Why? Well, because, of course, this is this is what you're doing. You have your function. Come on. Yeah, you have your function that you're trying to differentiate, which is something like this. And you are at a given point, maybe this one, and then also this is x. And then I'm exaggerating a little bit, just for the purpose of showing you. This is x plus epsilon or plus delta x, whatever. And now what you are doing is computing this difference here and dividing it by this difference there, such that you can find the slope between these 2 points, right? So you need to compute this difference here, this one. And this is over there, so this one minus that. However, observe, floating points have limited precision, meaning essentially that they have a limited amount of digits beyond the dot. Maybe here there could be an exponent 10 to the minus 10 or 10 to the 20, but the point here is not that. The point is the number of digits that you get after the dot, okay, which is about 15 or 16. Now, when you do the difference, you see that all of these first pieces here match with these. Actually, if you imagine that here there are zeros after the second one, you see that everything matches up to here. And what's left is just 7, 0, 2, 4. And however, right to the right of these, in principle, mathematically, there should be other digits if you compute this analytically, but we just lost them. We just lost them because when we did this computation, we had to keep track of these digits. We had to keep track of those, but now we are discarding them immediately. So we have discarded the digit to the right because we needed these ones, but then we are also discarding all of those. We are left basically with only 4 digits of precision. You look at this, and you don't see it when you see it represented in decimal, because the underlying representation is binary. But trust me on this piece here, minus 7.024, is the only thing that it's actually true. I mean, correct. All the rest is basically garbage. Where does it come from? It comes from the fact that there were a bunch of zeros in the binary representation, coming from the fact that here they were missing, in this one here, there were missing bits. They were thrown away. So there are zeros, and then when you translate it to decimal representation that Python does for us, you see those random digits, essentially. But they're not truly random, but for all our intents and purposes, they are random, they're garbage, they don't mean anything. And so you get wrong result, and you see that now you take this, you divide it by 10 to the minus 12, and this is your derivative, because that was epsilon, right? And this is your derivative, and now your derivative is basically only precise up to here. And all the rest is essentially garbage, is wrong, imprecise. Good. I guess my time is up. It's like boiling water or something. Okay. Yeah, so we'll see. I mean, just to conclude, there's not really a way out of this, okay? Not in this context. With finite differences, there's a trade-off. You either you increase the precision, but at some point you lose it. There's just no way out of this particular issue here. At some point, the function values does not change anymore, but epsilon decreases. That would be true. So for Dennis, that wrote something here, that would be true below another threshold in epsilon. Okay, let's stop the recording.